calcium oxide-based self-heating cans. These cans heat food by reacting chemically. This exothermic reaction is between calcium oxide and water. The packaging of these cans plays an important role in the function and design. These cans are designed to be a two-chamber system. The outer chamber houses the chemicals while the inner houses the food. A button may be pushed on the bottom of the can to release the water into the chemicals. Once this reaction occurs, the exothermic heat gives off into the inner chamber to heat its contents. They must be careful in designing these cans to be sure that the chemicals will not overheat, causing the contents to be spit out. They also must be careful to keep the chemicals out of the inner chamber so that the food is not infected by the chemicals. The reaction between calcium oxide and water forms calcium hydroxide, as you can see in this balanced chemical equation. The Lewis dot structure of calcium oxide consists of the valence electrons that combine the two. Calcium has 2 and oxygen has 6, which results in 8 electrons. So to distribute the dots among the two, the structure would look something like this. The Lewis dot structure for the other reactant, which is water, comes from hydrogen, which has 1 valence electron. Having 2 of those plus 6 valence electrons from oxygen recurs with 8, which is shown here in this dot structure. The Lewis dot structure of calcium hydroxide, which is the product, comes from the combination of valence electrons between calcium, which there are only 1, so that's 2 electrons from calcium, 2 from the hydrogen atoms, and then 12 total from the oxygen, resulting in 16 valence electrons. Since calcium is the central atom, all of the other elements form around that, and if they followed the octet rule, there would be too many electrons. So you have to add that double bond between the 2 oxygens and calcium.
Our estimated volume of the can is 8 ounces, which we converted to milliliters, and we use the heat capacity of water. The temperature change between 37 degrees Celsius, which is body temperature, and 20 degrees Celsius is 17 degrees Celsius. We then assumed that we were working with 100% heat transfer. The formula for heat is heat capacity times the mass times the temperature change. If instead of the original 100% yield, we were looking for the 80% yield, we would simply divide by 80 and multiply by 100.
To find 71% of calcium oxide, use the same previous steps that you would use when finding 80% yield. You take 35,863.29, divide that by 71, and multiply by 100. Your answer becomes 50,511.68 grams of calcium oxide mixtures. The can of the unknown alcohol contains 70% ethanol and 30% water, and we are expecting it to heat up at a lower temperature than the soup because ethanol's boiling point is at 78.37 degrees Celsius, while water reacts at 99.98 degrees Celsius. With that information, we concluded that the can would heat quicker at a lower temperature.
The reaction for the self-heating can calcium oxide is CaO plus H2O yields to CaOH2. The heat formation for CaOH2 is negative 986.09 kilojoules over moles. The heat formation of H2O is negative 285.8 kilojoules over moles, and the formation of CaO is negative 635.09 kilojoules over moles. The formula for heat enthalpy is products minus reactants, when 986.09 kilojoules over moles is subtracted by negative 635 kilojoules over moles plus negative 285.8 kilojoules over moles, it equals to negative 65.2 kilojoules over moles. Therefore, the enthalpy of the reaction is negative 65.2 kilojoules over moles. The reaction is exothermic. It is important for the reaction to be exothermic so that the substance may heat up properly. The self-heating can has a button, and when the button is pressed, the calcium oxide is then mixed. with the water causing the can to heat up. This product is important for campers, soldiers, hikers, and others who are always on the go. A disadvantage of this product is that it may cause uneven heating and is expensive. An alternative is to use magnesium metal and water. This is also an exothermic reaction with the formula of Mg plus 2H2O yields to MgOH2 plus H2. You work the product that uses magnesium metal and water by opening the bag and mixing both water and magnesium metal together. Then you place the food inside and seal the bag closed. A disadvantage for this reaction is that it may take up to as long as 10 minutes or more to heat up. Some benefits are that this reaction is used for food in the military on the go, and you can also heat solid food items as opposed to just soups and coffees.